Hello everyone, I'm Ömer. In this talk, I will give an overview of frequency modulation atomic force microscopy, or is it called FM AFM, and its significance in nanoscale materials characterization. We will explore how it works, why it's used, and where it provides a unique advantage in material science. To begin, SPM refers to a family of techniques used to image surfaces at nanometer scale. Atomic force microscopy, or AFM, is one of the most widely used SPM methods. It uses a sharp tip on a flexible cantilever to interact with the sample surface. The interaction is monitored via laser photodiode system, enabling surface mapping in various modes such as contact, tapping, or non-contact. So what is exactly FM-AFM? Let's break it down in the next slide. FM-AFM is a non-contact imaging mode in which the cantilever is oscillated near its resonance frequency. When the tip gets close to the sample, the tip sample forces modify the effective stiffness of the cantilever, causing a shift in its resonance frequency. A phase lock loop continuously tracks this frequency shift, and the system uses it as feedback to maintain a constant interaction. This method is especially useful for detecting subtle variations in surface force. This schematic illustrates the setup. The cantilever is excited via a piezoelectric actuator. Its motion is detected by a laser and photodiode. The signal passes through a preamplifier and is processed by a self-oscillation loop, including phase shifter, limiter, and gain controller. An FM detector monitors the frequency shift. A noise source can optionally assist in excitation for stability. Together, this system allows for precise control over tip sample distance without physical contact. Here we see the K equation governing FM-AFM. The frequency shift delta F is proportional to the gradient of the tip sample force. Even slight changes in the force gradient can result in measurable frequency shifts, allowing FM-AFM to detect atomic scale features. These force gradients may arise from van der Waals electrostatic or chemical interactions, making this technique extremely sensitive. So what makes FM-AFM so special compared to the other AFM techniques? Let's look at its main advantages. FM-AFM achieves atomic level resolution even on hard or insulating surfaces. Since the tip doesn't touch the sample, it avoids damage and tip wear, ensuring stable imaging. The technique performs best in ultra-high vacuum and at low temperatures, where noise is minimized. It also provides information on both conservative, elastic, and dissipative energy loss forces. You can also see in the lower figures how vacuum enhances current sensitivity compared to air and vacuum conditions. FM-AFM is used to study materials at the atomic level. On the left, we see an image of a potassium bromide crystal lattice. In the center, molecular level resolution is achieved, while the right shows stiffness maps of structured surfaces. These applications are valuable for analyzing polymers, coatings, nanocomposites, and 2D materials, like graphene and molybdenum disulfide. Reference 8 also demonstrates how electronic contrast and charge localization can be mapped at the molecular scale. To conclude, FM-AFM is a high-resolution, non-destructive microscopy method that enables detailed surface analysis at the atomic level. It combines mechanical sensitivity with minimal interaction forces, making it ideal for advanced material research, from basic cantilever setup to sub-nanometer imaging. FM-AFM demonstrates how precise physical control leads to profound insights. Here are the references I used throughout this presentation. These include recent papers on FM/AFM fundamentals, applications, and instrumentation, as well as selected reviews and experiment studies that illustrate its capabilities in material science. Thank you again for your attention.